Alright, hello, and here we have lecture 2.3. This is actually the last lecture in Unit 2, so we are already wrapping up Unit 2, and this section is over finance. So, as you probably noticed with most things in quantitative reasoning, this is not going to be a particularly deep dive, so we're going to kind of dip our toes into the world of finance. And it's here we'll begin with simple interest. So before discussing simple interest, we need to define principal. Principal is basically the initial value of an investment. When you borrow money, you will pay it back plus interest. So when you take a $1,000 loan out, you're going to pay back the $1,000 plus interest. In the case of simple interest, the interest payments will be some percentage of the principal. So that's the simple part of it. It's just a percentage of the principal. So let's look at an example here. First example of the lecture. Friend asks to borrow $400 and promises to pay you back plus 5% interest at the end of the week. How much will he pay? Well, he's going to pay back the $400, right? So he's going to pay that back, plus he's going to pay back 5% of what he borrowed, which is 5% of 400. So that comes out to $420. So at the end of the week, he's going to be paying you $420. So you get your $400 back plus that 5% interest. So this example demonstrates simple one-time interest, but many times interest is charged multiple times. So let's go ahead and look at this example. So if you go back and look at World War II and other moments in history, wartime bonds were a popular means for raising capital for the war effort. So wartime bonds are issued to assist with the war effort. You purchase a $1,000 bond that pays 3% interest annually, and it matures in 5 years. So that means by the end of the 5 years, they'll pay you back. So how much interest will you earn? Well, you're getting 3% of that $1,000, which is going to be, see here, I believe that's $30, which is $30 annually. So annually means each year. And you're going to get that each year for 5 years. So you will earn $150 in interest over the life of this bond. So you'll earn $150 in interest, plus you'll get your $1,000 back. Now, that 3% interest annually brings us to the concept of APR. So APR stands for annual percentage rates, and interest rates are usually given as an APR. So it's basically the total interest that will be paid in the year. So typically when we're talking about interest rates, we're actually talking about the APR typically. Now, a lot of times that interest will be paid in smaller increments. So in other words, that APR gets divided up. So for example, a 24% APR paid monthly would be 12 2% payments. You're basically going to get 1/12 of it at a time if it's monthly. So let's look at this next example. A company sells $2,000 bonds with an 8% APR paid quarterly with a maturity of 3 years. How much interest is paid quarterly? So it's going to be 8% per year. So that's the annual part of an APR. So it's 8% of the $2,000 per year, which comes out to $160 per year. So that's how much interest is paid out per year. Now you don't get it all at once. Instead, it'll be broken into quarterly payments. So you just divide that by 4, and that gives you $40 per quarter. So you're going to get $40 each quarter in interest. So that's how the interest works there. Now, how much interest will that be? Well, the maturity is 3 years. Well, you're getting $160 per year for 3 years. So that's going to be $480 in interest. And that's total for the entire life of the bond. So basically every quarter you're getting $40. Now the next question is, what if you take that $40 and reinvest it? Right? So instead of pocketing that interest payment, what if we reinvest it? Well, if you take interest and reinvest it, that is called compounding interest. So the reinvestment of interest results in compounding interest. You can see this on your credit card every month. So basically, suppose you have a 24% APR on your credit card, then it's going to be broken into 12 2% payments, and that percentage is applied to your balance, and you don't pay that interest every month, right? So that might be anywhere from, like, if you look at your credit card statement, it might be like $15, $20 in interest each month, and you don't have to pay them that interest right then. Instead, they take that interest, the credit card company, and they add it to your balance. So they are basically taking the interest and reinvesting it. That completely changes the mathematical nature of the model. So before, simple interest was a linear model, representative of linear growth. Compounding interest, when you start reinvesting that interest, results in exponential growth. And this is huge. So let's go ahead and see what it looks like. So suppose you got $1,000 with a 4% APR compounding quarterly. So after the first quarter, your balance started off at $1,000, and you're going to get 4% of the $1,000, which is $40. Oh, well, I'm sorry. That's not going to be $40. Sorry, it's 4% compounded quarterly. Almost forgot. So that means you got to break it into quarters, so that basically means you're getting 1% per quarter. So that's $10 in interest. So instead of getting a $10 check in the mail, that $10 is just added to your balance. So come quarter two, your balance is at $10.10. You're still getting 1/4 of that APR for the next quarter, which is 1%. But this time it's 1% of $10.10 instead of 1% of 100. And that comes out to $10.10. So you get a little bit more interest than you had before. So now your balance is up to $10.20 and 10 cents. And then quarter three, again, it starts off at $10.20 and 10 cents. You're still getting that quarterly 1%, but this time it's 1% of an even bigger number. All right. And that gets you approximately $10.20. So as you can see, it's not $10 in interest each quarter. You're getting a little bit more, a little bit more, a little bit more. So if we add that to your balance, you get $10.30.3. And you can see the idea here. Each quarter, it's just going to be a little bit more, and it's speeding up, speeding up, speeding up, speeding up. So it's not linear growth. Right? If it were linear growth, it'd be an increase of $10 every quarter. That's not what's going on here. It's $10, then it's $10.10, then it's $10.20. And you can see here, we'll do now 1% of this balance. And that gets us, a little over $10.30 if you round to the nearest cent. So we are now up to $10.40.6. So as you can see, it is speeding up a little bit, little by little. It starts off slow, but over time, this will become very impressive actually, once it starts getting a little bit of momentum. So I'll go ahead and stop here. Hopefully you can kind of see the idea of what's going on. So it'll be 10.51 right there. So in the short term, it's not a huge difference, but in the long term, it's a massive difference. Now, as you can see in that table, computing compound interest can be very tedious. The good news is we have a mathematical model for it. So here's our formula for compound interest. You'll definitely want to put this on a piece of paper and have it available to you when you're working through the upcoming test. So there's the formula for compound interest, where B represents the balance at t years, P is principal, R is APR, K is frequency of the compounding, and T is the number of years. So instead of having to do it, interest period by interest period, we can do it all at once. Now, a quick warning here. The most difficult part of this finance lecture and finance unit is just being familiar with your scientific calculator. You have to be precise. So if I type this into my calculator, 100 times 1 plus 2/3 raised to the 20, here's what I get. I will get 111.23. Alright, so I get 270. Ooh, no, my decimal's off. I get 2,735,111. So, alright, you get 2.7 million essentially. Now, you know that 2/3 is 0.6 repeating. So 2/3 equals 0.6666666 on forever. You're thinking, well, I know 2/3 is 0.6 repeating. I'm just going to round that to 0.7. Right? That's close, right? We can round 2/3 to 0.7, can't we? Well, let's see what happens here. This is the number we get here. Rounding to the nearest cent. And you can see here we have more than 4 million. Suppose we're talking about dollars here. You're talking about $2.7 million compared to $4 million. In other words, way off. Way off. Not even remotely close. All because we rounded 2/3 to 0.7. That was rounded correctly, but it still threw your answer way off. In other words, I can't stress this enough. You need to know how to type fractions into your calculator. You have to know how to type fractions into your calculator, or you're not going to be even remotely close to getting the correct answer. So you have to be very, very precise with your calculator here. Let's go and look at this first example. Suppose you got $3,000 is invested into an account with a 7% APR, compounding monthly. Compute the balance in 22 years. So let me go ahead and write the formula here just for reference. So the balance we don't know, so it's going to stay as B. The principal is 3,000. 1 plus the rate. The rate is 7%, so that's 0.07. Divided by K. It's compounding monthly, so the period is months per year, so that's 12. And we got 12 up there, and it's for 22 years. So suppose we have $3,000 invested in this account for 22 years. We just invest the $3,000, then ignore it. And you should be getting, rounding to the nearest cent, $13,931.30. So just under $14,000 is the answer here. Now, I highly recommend type this into your own calculator. Verify that you get this same number that I do. Recommend you press the pause button and do this. Make sure you know how to type fractions and exponents into your calculator. If you don't know, look it up or seek out assistance. It's very important that you know how to use your scientific calculator for this unit. Let's look at another example. Suppose you know you're going to need $40,000 for your kid's education in 18 years. If your account earns 5% APR, compounded quarterly, how much principal is needed? So, still the same compound interest formula. There you go, rewrite the formula there. This time we know we want the balance to be $40,000, but we don't know the principal. So we'll leave that as P. We know the interest rate is 5%. It's compounded quarterly, so K is 4. And it's going to be for 18 years. So what we're going to go ahead, we're going to have to solve this equation. So that's P times, and then we're going to type that number into our calculator. So again, I recommend you press the pause button, type this in yourself. Make sure you're getting the same number as me. You should be getting 2.4459. We'll take it to 4 decimal places. 2.4459, and then divide both sides accordingly. And you get principal is approximately 16,353.90. So you would need approximately $16,000 in principal invested, and in 18 years that $16,000 would become $40,000 approximately. Now, is this realistic? No, this is not how we realistically save money, right? We typically don't have one big giant deposit that we throw into a retirement account or a savings account and forget about. This is not realistic. What is realistic is an annuity. So when saving, we don't normally make one big giant deposit. We normally make smaller deposits on a regular basis. So, right, instead of, for our kids' education, we're not going to be able to throw $16,000, $17,000, or $18,000 into an account and then ignore it for 18 years and then it'll be good to go. No, instead we might be able to tuck back, maybe $100 or $200 a month and see where that takes us. So basically what we're describing here is called an annuity, and I highly recommend you read those book pages listed there. The book derives the formula, so you can actually see where the formula comes from. Instead of deriving the formula, we're going to focus on using the formula. So the formula is listed there, and we're going to go ahead and play with it. B represents the balance at T years, D is your periodic deposit, R is the APR, K is your frequency of compounding, and T is number of years. Now, the annuity formula and every formula from this point forward is going to assume that the frequency of the deposits matches the frequency of the compounding. So because of that, the default is going to be 12, in other words, monthly. So suppose that you deposit $100 each month into an individual retirement account, or what we call an IRA, with a 6% APR. What will the balance be in 30 years? So we just punch it into the formula. So we don't know what the balance is, so we'll call it B. We know that the deposit, or D, is 100 times the quantity 1 plus the rate. We know the rate is 6%, so that's 0.06. We're paying monthly, so it's 12. Raise the 12, and it's for 30 years. Minus 1, all divided by 0.06 over 12. So let's go ahead and type this into our calculator. So at this point, feel free to press the pause button and type it into your own calculator just to verify that you know how to type this in. So here. And you should get, rounding to the nearest cent, 100,451.50 cents. There we are. So that's the number you should get typing into your calculator. So in this case, with a 6% APR and $100 every month for 30 years, that balance will come out to $100,000 in this retirement account. So how much interest will you have made? Well, let's look at that. So how much did we pay? So we paid $100 each month, so that's 12 times a year for 30 years. So we paid, or we deposited, I should say, $36,000. Oh, we deposited $36,000, but we're ending up with a little over $100,000. So we take the difference. So our balance will come out to $100,000, $451.50, minus the $36,000 we deposited. And there we'll get our answer. So over the 30 years, this has earned $64,451.50 in interest. So you actually earned more in interest than was even deposited. A lot more. So this is why when you're saving up for a retirement account, you are depositing that money into a retirement account instead of shoving it underneath your mattress. If your retirement plan was to shove $100 underneath your mattress every month for 30 years, you would end up with $36,000. Now that's not insignificant. That's a lot of money, $36,000. Or what if you made like a separate checking account where you don't ever withdraw from it, you just deposit $100 a month for 30 years, then the balance would be $36,000. But if you have it getting interest and it's compounding interest, like an annuity is, then you're basically throwing away $64,000 in interest, right? If you don't go to deposit into this particular retirement account. Let's go ahead and look at another example. So it'll be the same formula, still the annuity formula, but we want to have $150,000 in the account when we retire in, say, 25 years. APR is 4%. How much do we need to put in there each month to meet that goal? So this time we know the balance is $150,000, but we do not know the periodic deposit, so we'll leave it as D. So then we'll go ahead and just use our formula. If you need to flip back, it's on the other page. So that's 1 plus the interest rate, which is 4%, monthly deposit. So raise the 12, it's for 25 years. Times 25, and then minus 1, all divided by 0.04 over 12. All right, cool. So there it is. So we're going to go ahead and just type that number into our calculator. So feel free to press the pause button. You're going to get D times, let's find out. And we get, let's see here, 514. We'll go to 4 decimal places. 1295. So that's the number you should be getting. And then we'll just divide both sides to get D by itself. This will give us a pretty decent approximation. And we get, let's see here, D is approximately, rounding to the nearest cent, 291.76. So if we wanted to retire with $150,000 in 25 years, we would need to be depositing a little over $290 per month to reach that goal. Alright, so that's how we play with annuities, which are your standard retirement accounts. But what about after retirement? So you're no longer getting paid by your employer. Instead, you're going to start paying yourself. So that leads us to a payout annuity. A payout annuity is a normal annuity, except instead of making periodic deposits, you will be making periodic withdrawals. You'll be paying yourself every month. So when you retire, you don't want to pull all that money out of the retirement account, right? Suppose you got $150,000 in your retirement account. You're not going to pull that out and transfer it all to your checking account. That would be foolish because that retirement account is still earning interest. So you want to milk it for all that it's worth. So we're going to leave that and only transfer out a small amount each month. We're only going to withdraw as much as we need, so to speak. So here's our payout annuity formula. So it's like a retirement account, but instead of making periodic deposits, it's all about periodic withdrawals. And there's the formula there. Alright, so let's look at this example. Suppose you want to pay yourself $3,000 every month for 15 years when you retire. How much money would you need if you were not earning interest? So if you're not earning interest, how much money do you need? Well, you would need $3,000 every month, so 12 times a year for 15 years. So if you're not earning any interest, this is the amount you would need. $3,000 a month for 15 years. That's $540,000. That's a lot. That's a lot. All right, if you're not earning any interest, you need to have a checking account with $540,000 in it in order to pay yourself $3,000 a month for 15 years. All right. Well, that's a little bit ludicrous. Let's see if we get that number down a bit. So suppose you have a retirement account that earns 5% APR. Then how much do you need? So let me go ahead and write our annuity formula. So it's initial balance equals withdrawal times 1 minus 1 plus R over K raised to the negative KT. Don't miss that negative sign right there. It's very important. All over R over K. Now, it's very important that when you're looking at the payout annuity formula, that this is the initial balance, all right, when it starts. So how much do we need? We don't know. So we'll leave that as a letter B. We want to withdraw $3,000, and we're doing it monthly, and the interest rate is 5%. So just using the formula here, negative 12, it's for what, 15 years, all over 0.05 over 12. So all we got to do is type that into our calculator. So if we don't have any interest accruing over that period, we need $540,000. But if we withdraw from the retirement account and leave money in the retirement account so it still earns interest, let's figure out how much we'll need. So go and type that into your calculator. And you can see that number plummets down to this. All right, $379, $365, and 73 cents. So instead of needing $540,000 saved up, you would need $380 roughly, and that would be enough for you to pay yourself $3,000 a month for 15 years after retirement. So how much interest would you earn over those 15 years? Well, if you want to think about it, your balance starting off would be $379,365 and 73 cents. But we're going to be withdrawing $3,000 every month for 15 years, which we already computed that. That's $540,000. So even though we retired with $379,000, we're going to end up withdrawing $540,000 if we leave it in there and let it still earning interest. So how much interest is that over those 15 years? We'll just take the difference. Let's see here. And that comes out to $160,000. So in other words, if you were to take your entire retirement, all your retirement money, and transfer it out of your retirement account and move it to an account where it's no longer earning interest, at least in this case with this APR, and for 15 years, over the course of 15 years, you'd be throwing away $160,000 in interest. All right, last formula. The loans formula. Now, if you look closely into this formula, you realize it's no different than the payout annuity formula. And you'd be correct. It's exactly the same. The only difference is your monthly withdrawals are monthly payments. And the balance is still decreasing, because that's the idea with a loan. You're going to keep paying on it until that balance hits zero. Same thing with a retirement account. You're going to keep withdrawing from it until that balance hits zero. So, suppose you can afford $300 a month for a car payment, and you're pre-approved for a 3% APR 60-month car loan. That APR is a little bit low. Let's use a more realistic APR for car shopping. Let's change that to an 8. Let's go with an 8% APR. So suppose with your credit score, you're approved for an 8% APR, 60-month car loan. So that is a 5-year car loan. Let's take a look at it. So how expensive a car can we afford? So we don't know what the principal of the loan is, so we leave that as a letter. We know we're paying $300 per month. 1 minus 1 plus. The rate is 8%, so that's 0.08. Making monthly payments, so that's a 12. Raised to the negative 12, and it's a 5-year loan. So don't input 60 there. Remember, this time variable in all finance formulas, or at least most finance formulas, is in years. So 60 months, that's 5 years. All divided by 0.08 over 12. So all we got to do is type that into our calculator and see what you get. So feel free to press the pause button, practice this on your own. Highly recommend you practice this on your own. Do not wait until the test to see if you know how to type this into your calculator. You'll be inviting disaster. And it comes on out to $14,795.53. So if you want to go with a 5-year car loan and you want your monthly payment to be at $300 and you got an 8% APR, that's the most expensive car you can get, keeping your payments at $300 a month. So right around $15,000. Now, how much interest will you pay? Well, let's figure out how much you're going to pay. All right, because you're not going to pay back the $14,795. You're going to pay that back plus interest. So you're going to be paying $300 every month. That's 12 months per year for 5 years. So you're going to pay $300, not $3,000. Off by order of magnitude. $18,000. So that's how much you're going to pay back. So you're going to pay the bank $18,000 back over the course of those 5 years for them loaning you about $15,000. So to figure out how much interest that is, you just take the difference. So you're paying $18,000 for a $14,795.53 loan. So that means you're going to be paying $3,204.47 in interest. So you're going to be paying about $3,200 in interest for this car. Let's look at another example. Let's look at mortgages, home loan. Suppose you want to take out a $200,000 mortgage, APR is 4%. Let's look at the 30-year loan. What will your monthly payment be? So we know the principal is $200,000. We do not know what the monthly payment is, so we'll call it a letter. And looking at our loan formula, it's going to be 1 minus 1 plus the rate, which is 4%. Monthly is 12, raised to the negative 12 for 30 years, so the t value is 30 all over 0.04 over 12. So that's going to be $200,000 equals D times, and we got to type that number into our calculator. So let's go ahead and do that. Don't forget the negative sign in the exponent's place. Very easy to miss that. And that's 209. We'll take it to 4 decimal places. 4612. 2. And then just divide both sides by that value. You get a monthly payment is going to be about $954.83. Now, just a heads up, this is not including your property tax and homeowners insurance. This is just for the loan. So that would be how much your monthly payment would be. Again, that's just for the loan, not including the escrow. All right, we're just looking at the basics here. So you'll be paying that every month for 30 years on this loan. So how much interest is that? Well, you're going to pay $954.83 every month for 30 years on this loan. So that's going to come out to $343,738.80. How much was the loan for? $200,000. So in other words, you're going to pay back $343,000 for a $200,000 loan. So in terms of interest, you just take the difference. So that's going to come out to $143,738.80. So that's how much you're going to pay back for that home loan. If you go with a 30-year loan, that's how much interest you're going to pay. Now let's compare that to a 20-year loan. What will your monthly payments be for a 20-year loan? So we know that for a 20-year loan, you're going to pay more per month than you do for a 30-year loan. But how much more? Let's find out. The loan's still a $200,000 loan. That doesn't change. Monthly payments, we don't know that. We're trying to figure it out. The APR is still 4%. That has not changed. The exponent is now for 20 years, not 30, so that number is different. All over 0.04 over 12. So if you're clever with your calculator, you don't have to retype all that in. Just scroll up to where you had the previous input and just change the 30 to a 20. That's all you got to do. And you will get a very different number. So that's going to be D times 165 point. Let's take it out to 4 decimal places, 0219, and divide accordingly. So now your monthly payment is going to come out to $1211.96. So in other words, you're paying like an extra $240-ish per month. So you're paying more money per month, right? Your monthly payment jumped from $950 to $1,200 essentially, roughly speaking here. But how much interest will you pay for the 20-year loan? Well, you're going to be paying that $1211.96 every month for 20 years. So that means over the course of the mortgage, you will pay $290,870.40. So you can see, if you compare that to Part B, that's way less. So here, how much interest are you going to pay for the 20-year loan? Well, you're still getting a $200,000 home, but now you're paying $290,000 for it instead of $343,000 for it. So that's going to come out to $90,870.40. So go ahead and compare those two numbers. If you go with a 30-year mortgage at a 4% APR, and that's pretty close to the national average right now. So that's a pretty realistic APR. $200,000 home, that's pretty normal around here. You know, it's a pretty standard price for a home, for a good home. So for a 30-year mortgage, you're going to be paying $143,000 in interest, whereas for the 20-year mortgage, you're going to pay $90,000 in interest. So you're saving roughly $53,000 by going with the 20-year mortgage. What's the trade-off? Your monthly payment will be higher. That's the trade-off, by about $200 a month. Is it worth it? Well, you'd have to think about that yourself. Right, is that extra $200 a month worth saving $50,000 in the long term? You decide. All right, last example. Now, something you need to be aware of, only a portion of loan payments go to the loan balance. A portion is going towards interest. You do need to be aware of this when you're making loan payments. So let's suppose a couple purchase a $180,000 home at a 4.02% APR. It's a 30-year mortgage. Compute the monthly payment, no escrow, so just the monthly payment. Alright, so this is the same thing we just did. $180,000 is the principal. Monthly payment, we don't know. Interest rate is 0.0402 all over 12. Raise negative 12, it's a 30-year mortgage. So let's go ahead and solve that. 0.0402 over 12. And if you solve that equation, you will get approximately, so let me type that in real quick. you are going to get approximately $861.42. So that will be your monthly payment on that loan. $860 per month is your monthly payment. So compute the remaining balance on the mortgage after 7 years. So you got to be very, very careful here. This is not as simple as, taking 7 years of payments and subtracting it from $180,000. Because if you do that, you would be completely ignoring the interest, and that's huge. So what you need to look at this as is, you can view this as kind of like, now it's a 23-year loan. Right, you're 7 years in, so you can view this as a 23-year loan. You don't know what the remaining balance is. So we'll call it P for the remaining balance. We don't know what it is, but we know our monthly payment is $861.42, and then all the other stuff is the same interest rate, 0402 over 12 raised to the negative 12. Now the number of years is now 23. That number there is different. It's no longer a 30-year loan. We're 7 years in, so there's 23 years left. So you plug in 23 and evaluate that. And all you got to do is punch that into your calculator. Let's see what we get. So, and here we go. We get $154,977.55. That's the remaining balance on the loan. So 7 years in to the loan, that's how much of the remaining balance you have. So what we need to look at here is, where are your payments going? Right? If you look at that, the balance seems higher than you would think. And if you've had to deal with a car loan or a home loan, after a few years, you might look at that balance on your statements like, man, that seems really high. Why is that balance so high? I've paid more than that. Well, you got to take into account the interest. So in 7 years of ownership, how much interest have you paid, or this couple? Well, they have been making payments for 7 years, so they've been paying $861.42 for 7 years, and it's 12 months per year. So they have paid $72,000. Let's be precise here. So that's how much money has been paid in those 7 years, more than $72,000. Now we can't just subtract that from the $180,000. So what we got to look at is the change in balance. So the balance of the loan started off at $180,000. 7 years later, it's down to $154,000. So we figured this out in part B. And we're going to get, let's see here, type that in the calculator, $25,092.51. That's how much money has actually gone to the principal. So the $72,000 you've paid over those 7 years, out of all that money you've paid, $25,000 has gone to the principal. The rest has gone to interest. All right, that's where you got to be careful. All right, so we've paid. Or hold on, let me double check that number. 25,000. Sorry, I misread my calculator. 22 is off just a little bit. So that's how much money we've paid over that point in time. But where the interest is paid, well, we've paid $72,359.28, and out of all that money we've paid, $25,000 has gone to the principal. The rest has gone to interest. So that tells us we have paid out of that $72,000, $47,336.83 has gone to interest. So this is why it's a catastrophic idea, financially speaking, to buy a house and then immediately try to dump it or get rid of it after just owning it for a couple of years. In many cases, it depends on how the market's going. There's a lot more variables in play, but your balance is not going to be as low as you think it is. That's because a big, huge chunk of your payments, especially at the beginning, is going towards interest. Right. So you can see in the first 7 years, most of the money has gone towards interest, actually. All right, in those first 7 years, we've had $25,000 going to the principal, about $47,000 going to interest. So that's just the nature of loans. This isn't some conspiracy theory. It's just the nature of the math. The interest is going to be rather front-heavy, right? You're going to be paying the lion's share of the interest in the first half of the loan. So the beginning of the loan is where you're really paying off the interest quite aggressively, and it's later on in the loan where a bigger portion of your payment's really going towards the principal. So in summary, this is just a quick little tip on when to use which formula. So if you're going to use the compound interest formula, that's one deposit and interest is compounding. Of course, if it's not compounding, then that's simple interest. An annuity is periodic deposits that are increasing the balance. A payout annuity is periodic withdrawals, which are decreasing the balance. And of course, a loan is periodic payments decreasing the balance. Alright, that's a wrap for this lecture, and we are done with Unit 2, so please start working on that test review as soon as possible, and have a good day.